This is problem number 30 from out of section 2.3, and in this problem we're given a function that represents the height an object is off the ground as it's traveling upward and then back downward to the ground. What we want to do is we want to compute velocity and acceleration functions for this object. We want to then use the velocity and acceleration functions to compute the velocity and acceleration at, in the case of number 30, t equals 2. And then we want to answer these couple questions. Is the object going up or down? Is the speed of the object increasing or decreasing? What we need to utilize in order to answer these questions is we need to think back to something that we'd mentioned in class. If h represents the position of an object, how high it is off the ground, the derivative of h is going to represent the velocity function, and then the second derivative of h, which would be the first derivative of velocity, is going to represent an acceleration function. So what I want to do first here is I want to find my velocity and acceleration functions. So h prime of t is going to give me a velocity formula. And if I take the derivative of this using the power rule, I'm going to multiply this coefficient by that exponent, and I'm going to get a negative 32. And then I'm going to subtract 1 from that exponent, so it's going to be negative 32 t to the first. And then if I use the power rule on this, multiply by that exponent, I'd get a positive 40. And then if I subtract 1 from that exponent, it's a t to the 0, and if it's a t to the 0, you don't have to show it. And then the derivative of a constant is 0. In physics, you don't normally measure anything in English units, but this is actually the acceleration of gravity in feet per second squared. But this is the slope of our velocity formula. So our velocity formula ends up being linear, right? No exponent left on the t. I'm also going to compute my acceleration function before I answer any of the questions that were asked. And acceleration is going to be the second derivative of position, which corresponds to the first derivative of velocity. So here's my acceleration function. If I use the power rule on this negative 32 t to the first, I'm going to multiply by the current exponent and get a negative 32. I'm going to subtract 1 from that exponent. It's going to become a t to the 0. If it's a t to the 0, you don't have to show it. And then the derivative of 40 is 0. So like I said a minute ago, if the object is just going up and then traveling back down toward the ground, the only force acting on it would be gravity, and this is going to be the acceleration of gravity measured in feet per second squared, even though that wasn't really mentioned anywhere up in this set of directions. But this is, a realistic scenario here. It's not just some formula that our book came up with and threw our way and say, hey, here, answer these questions. This is actually the acceleration of gravity in feet per second squared. So as you're going into engineering, you might be seeing a lot more of that number in the future. But what we want to use this to do, what we want to use these things to do, is we want to compute the velocity and the acceleration at t0. And our t0 is 2. So we want to know what the velocity is at 2. We want to know what the acceleration is at 2. Once you have these functions, it's just a matter of evaluating to find the specific velocity value you need and the specific acceleration value you need. So the velocity value is just going to be negative 32 times 2 plus 40. And if you do the math here, I think that takes you to negative 64. And if you have negative 64 plus 40, that should leave you at, what, negative 24 for the velocity. And since this is likely measured in feet per second squared, this would be measured in feet per second. And I know units weren't specified at all here. I'm just going to toss them on just because that's what you're used to doing in physics, and it's just a good habit to be in. And then the acceleration, well, there's no t to put this 2 in place of, so the acceleration is just constant. It's just the acceleration of gravity in feet per second squared. So here would be our velocity at 2. Here would be our acceleration at 2. The questions were asked, is the object moving up or down? Well, based on what you know from physics, that question should be pretty simple. This object's moving down because this negative velocity indicates that the height is decreasing. The height is getting closer to 0 or closer to ground level. So this object is definitely moving down. Negative velocity indicates that. Is the object speeding up or slowing down? To answer this question, what I usually like to use is a quick sketch of what the velocity graph is going to look like. near the value we need to be concerned with. So I'm trying to think about what my velocity graph's going to look like. Now, my velocity function's linear, right? So I have a y-intercept that's going to be, you know, way up here, positive 40, and I have a slope of negative 32. So I'm going to have a pretty steep negative slope. And I know based on this number right here that on this velocity graph, at t equals 2, my velocity is going to be negative 24. So I'm just going to come down to negative 24 on my v-axis or on my y-axis, put a point there, and I need to draw something that's linear, right? So at this point, I know my velocity is negative 24, and the slope of that velocity formula, or that velocity function, is negative. And we kind of knew that based on this. The derivative of velocity was negative 32. The slope of this line is negative 32. Because velocity is negative, and becoming more negative, and speed equals the absolute value of velocity, since velocity is moving away from 0, the absolute value of it is getting larger, and therefore speed would be increasing. Hopefully this helped. We'll definitely be doing things with velocity, acceleration, position off and on all year long.